Okay, so it's 1 p.m. now. I think it's good to start. It's my honor to introduce Professor Ehud Altman from UC Berkeley. He is a leading expert in the condensed matter theory, particularly in the many-body physics of cold-atom systems and quantum information theory. So please join me in welcoming Professor Ehud Altman.
Okay, now it should be okay. So I'll try to make it accessible and give some broader review of what are measurement-induced phenomena and why they're interesting and new. And I want to thank collaborators that contributed to work that I'm going to talk, various works I'm going to talk about. My students, Yimu Bao and Zach Weinstein. Yimu is already a postdoc in KITT in Santa Barbara now. Soonwon Choi, that was a postdoc and is now faculty in MIT. Sam Garrett, who is still a Moore postdoctoral fellow. And Anna and Rohit are two undergraduate students in Berkeley, and both have gone on to graduate school in Harvard. So basically, the broad background is that new platforms, new experimental platforms allow to get much more detailed information about quantum states than we're used to. Examples they allow to measure entanglement entropy and information quantities more generally. Recently, there have been some, really interesting direct measurements of topological order by using Rydberg arrays, basically by measuring a type of correlation function that is really not accessible to usual condensed matter systems. It really measures some kind of loop operators or string correlation functions. So directly measuring the topological order in a state. Another really famous experiment that showed, that you can probe, deep corners, if you want, of the Hilbert space is this experiment by Google, the so-called quantum supremacy experiment. What it really measured is that the quantum state is a many-body entangled state that has a superposition of a large number of states in the Hilbert space that show many-body interference effects. That's really what they were measuring. It's basically a quantum circuit that, in the end, measured outcomes of, basically measured multiple qubits after passing through a deep quantum circuit, and showed that the statistics of the measurements have to show some kind of speckle pattern that is generated by quantum interference. But it's quantum interference not of a single particle, but of an exponentially large number of states in a many-body Hilbert space. This device, as well as quantum devices made of using ion traps, are now also able to make measurements not only at the end of the calculation, but what's harder to do in mid-calculation, mid-circuit measurement. So this actually provides a very interesting direction to explore the role of measurements in quantum mechanics, which is very unique, as you know. So far, traditional experiments have really not tapped into this aspect of measurement in quantum mechanics. In traditional experiments, measurements are used as a diagnostic of the quantum state. An example is a neutron scattering experiment. To scatter neutrons, they measure the quantum state that they interact with the quantum state, and the measurement outcome you get on the detector, you repeat the measurement many times by sending many neutrons, and at the end, you get some picture related to a particular property of the state you're trying to measure. So measurements are really used as a diagnostic. But if you remember, in quantum mechanics, measurements are more than that. So if you have a measurement in quantum mechanics, it projects the state. There is a quantum collapse of the wave function into a state that depends on the measurement outcome. So measurements actually invoke a sort of non-unitary evolution on the state that prepares a new state. And while unitary evolution has the notion of locality, and basically if you evolve unitarily, there is some kind of light cone, and correlations cannot change beyond beyond the light cone, even in non-relativistic systems. The strange thing about measurements is that when they act on entangled states, they can have truly non-local results, truly non-local effect. For example, well, I'll show you in a minute, but as you know, if you have a Bell state, if I measure one of the partners in the Bell state, I change the entire wave function. I eliminate a correlation that used to exist, and now after the measurement does not exist. There is another aspect of the measurement, of course, which is probabilistic. So every time you, so this is an example of this circuit where along the way I make measurements, and let's say I get a series of outcomes, 1, 0, 0, 1, 1, 1. With this these outcomes, I generate a particular quantum state, let's call it psi m, that depends on the series of measurement outcomes that I got. And every time I'll do the experiment, I'll generally get a different state because the measurement outcomes are random and depend, according to Born rule, on the expectation value of the projector of the wave in the wave function on the particular measurement outcome. So basically what I'm creating by doing measurements is I'm creating an ensemble of states every time I get a different state. But if I start from a pure state, it always remains a pure state. That's a big difference compared to usual open system dynamics. If I really care about the measurement outcomes, if I know what are the measurement outcomes, I know that I'm on a particular branch, and on that particular branch, what I get is a pure state if I started from a pure state. Okay, so here is what I said, that the effect of measurement is non-local, and this is what I said in words. The measurement implements a time evolution on the wave function that basically involves a projection on the particular eigenvalue of the measurement operator. And this is just a normalization. Actually, this normalization, what's inside the square root is the probability of getting that particular measurement outcome labeled here by Newton, right? This is the usual Born rule in quantum mechanics. And the interesting thing is that it kind of prepares a state. It's a type of time evolution. One of the two fundamental time evolutions in quantum mechanics, one is unitary, the other is this postulated measurement collapse that's non-unitary. And as we know, the measurement can change correlations non-locally if it acts on an entangled state. So if I have a Bell state and I measure only the left part of it, it destroys the correlation no matter how far these two were. And not only can measurement destroy quantum correlations, it can also create non-local correlations that did not exist. Here is an example. This is a setup usually I can think of as quantum teleportation setup, but for now, it doesn't matter. let's say we have two Bell states. One Bell state is shared by a laboratory here in China and another one in, let's say, in Berkeley. And so this is China and Berkeley. And then there is another Bell state that's shared by the same laboratory in Berkeley and some laboratory in the East Coast of the US, okay? And if I do a measurement in the laboratory in Berkeley on the, and measure, for example, here in the Bell basis, I will collapse the wave function on one of the Bell states. Let's say there is a label here because it can collapse on, according to Born rule on any one of the Bell states. And that will kind of immediately imply that this, these two atoms will also be in a Bell state with entanglement between them, shared by the lab in China and the lab in the East Coast, right? So I've created entanglement that was not present before just by making the measurement. I did the measurement completely locally, and instantaneously I created a very long-range correlation. This non-locality is pretty amazing, and that's what kind of disturbed Einstein. And it disturbed him when it was applied to two particles. And now the big question that now we're asking ourselves is, how do these kind of really strange non-local effects manifest when you act on an entangled many-body state rather than just a single Bell pair, okay? An example is, here is a many-body state of a quantum magnet that's entangled. What happens if I measure some of the degrees of freedom? How does it affect the other degrees of freedom? And here there is an opportunity for completely new types of collective phenomena because of the non-locality of this effect. Yeah. Yeah. I'll get to that. So for now, so absolutely. So here you need to actually see the effects that I'm talking about, as I'll talk about later more in detail. It's very hard to see because to see this non-local effect, I need to be in a particular branch of the wave function, and I cannot repeat that branch. I can never get the same state in my hand because every time I do the experiment, I'm going to prepare a different state. And in order to diagnose a quantum state, we know we need many copies of it. So in order to get many copies, I need to repeat my experiment an insane number of times until I get a repetition of the same measurement outcomes. If there are many measurement outcomes, that will be exponentially unlikely. And that's what's called post-selection. So to actually diagnose the state I'm getting, it seems like I need post-selection. This is something very important to understand. In the first part of the talk, I'll sort of ignore that this is what you need. And these are the older results that I'll talk to that are interesting, but always you have to keep in mind, if you're a mathematician, maybe you don't care. I mean, okay, so you wait an insane amount of time. You don't do experiments anyway, really. So, but if we want to do experiments, then we should care about it. And actually, I think that whether you can circumvent the post-selection problem in certain cases in some way, you cannot solve it, actually. You can circumvent it in some kind of cheating way that is very interesting at fundamental level, I think. And that's what I'm going to talk about towards the end of my talk. But yeah, you hit really the nail on its head. This is really the most profound issue here, that to see something interesting that's beyond just what is an open system, I really need to post-select or do something that is tantamount post-selection. Yeah, so here is the outline of the talk. This is just the time to say it. So first of all, I'll give some overview of what are the phenomena, measurement-induced phenomena, and how you can understand them. It's nice that these are complicated dynamical problems that involve both unitary dynamics, measurements, and so on. Amazingly, you can simplify a lot of that if the circuits you are dealing with are random circuits. you can use the randomness to derive a statistical mechanics model that describes a lot of these nice phenomena. And understand, at least at the qualitative level, and quantitative to some degree, a lot of these phenomena. So the first thing I'll discuss so-called measurement-induced phase transition and how to describe it. And second, I'll show a different class of measurement-induced phenomena, which doesn't have any dynamics, where you take a quantum ground state and measure some of the degrees of freedom, leave others unmeasured, and ask the question, how does measuring part of your wave function affect the correlations and the other parts? And that becomes particularly interesting in a case where this wave function is quantum critical. It's described by some kind of universal power law decay of correlations. And the question is, can you change the power law decay and change the critical behavior when you measure some fraction of the degrees of freedom? The ones you measured basically go out of the problem because they're quenched to what you measured. But the other degrees of freedom you haven't measured are still entangled and have some correlations. And the question is how they are affected. And in the last part, I'm going to discuss how to observe this phenomena circumventing the post-selection problem. Absolutely, yeah. So it's a really excellent point that you can actually discuss a class of classical problems with classical distribution where you just condition on the distributions. Here it's conditioning on measurement outcome. It's a little bit more involved so some aspects are different than conditioning on a probability distribution. Now it's conditioning on a wave function. Yeah, absolutely. Okay, so here is the setup for the measurement-induced transition that people looked at since about 2018. The simplest setup is you have a one-dimensional array of qubits. You start from a pure state, for example, this trivial state, product state, all zeros, and time evolve it with two types of time evolution. You have a brick wall circuit of unitary gates. These are the unitary gates. And to simplify the problem, the unitary gates are random from one point to another. So we're interested in some ensemble of circuits. But for every experiment, I'll have a particular circuit in mind. It's random, but when I do it one experiment after another, it's always the same random circuit. Okay, that's important. And intermeshed between these unitaries, there are measurements. So from time to time, we projectively measure some qubit here. So there is some finite probability of putting a measurement on any qubit here in space-time. And this is the evolution I mentioned in this case. Okay, so this is the time evolution. And as I mentioned, this time evolution basically constructs an ensemble of quantum states that are labeled by the measurement outcome. And what is the question? So the question that these people ask themselves, which I think is very interesting, although I'll show that it's, you can ask it in different ways, but the first way it was asked is the following. So if you look at this circuit and have no measurements at all, you can ask how the entanglement between the left half and the right half of the system evolves in time. We know quite well that the entanglement just simply increases. Every time you have a unitary gate, here it increases by the entanglement by one notch, and the entanglement more or less grows linearly in time until it saturates on the largest entropy you can get, which is just proportional to the volume of the subsystem. In this case, because it's one-dimensional, the subsystem, it's proportional to the length of the subsystem. Okay, so this is volume law entanglement entropy. But on the other hand, the intuition is when I measure a qubit, I disentangle it. Suppose I go to the extreme limit where after every cycle of unitary gates, I measure all the qubits, then I completely disentangle the state, and on average, I have some kind of area law entangled state, or maybe even not entangled at all. So the question is, they ask themselves, at least initially fairly naively, is whether there is a phase transition between time evolution that gives rise to a volume law state after a large time in steady state, and a state that has area law entanglement. So it's like a transition in the complexity of the state. And the result, and of course, you expect a sharp phase transition only in the thermodynamic limit where the number of qubits goes to infinity. And well, numerics show quite clearly that there is a transition. You can do the scaling, but here before the scaling, it's already kind of clear that at large measurement rates, you saturate to an entanglement of order 1, and eventually you go to entanglement that never saturates, and well, saturates only at very long times to volume law. And you can do finite size scaling and get really beautiful exponents and scaling collapse and convince yourself that there is a phase transition here. Yeah, the time is the depth of the circuit, right, which is kind of tight. Yes, yeah. Which way it's going? Yeah. Okay, and I won't describe exactly how, but there is a really beautiful mapping. If the unitaries are if the unitaries are random and independent of each other, and the measurements also give random results based on Born rules, you can utilize that too, then you can map this dynamical problem to a statistical mechanics problem where every unitary is basically, roughly speaking, every unitary is replaced by some classical spin, degree of freedom. That spin is kind of complicated. It can get values that correspond to different permutations rather than just up-down, but it's sort of like a quantum spin. And the evaluation of various quantities, like the entanglement entropy, boiled down to evaluation of the free energy of the system with different boundary conditions. I can give some intuition of why this is the case, why this is what you get. The reason basically is that when I calculate time evolution in quantum mechanics, I can think of it as a path integral. And when I have unitary evolution, random unitary evolution, if the unitary is random, then let's say then I have to calculate time evolution of some operator, let's say the density matrix. I have to apply the time evolution on both sides. So I have the forward time evolution on the left, and on the right I have a time evolution to backward time evolution. In this simple case, when I need to calculate just a single density matrix as a function of time, then when I do random unitary, actually the most important parts of the path integral in what is called the diagonal approximation is when the forward and backward path on the unitary are the same. Otherwise, they pick up random phases that kill themselves. So only when the forward and backward branch are the same, you don't kill, you have a constructive interference. Here, you have, when we calculate entanglement entropy, we actually can't just calculate the time evolution of a single density matrix because we need to calculate something like trace of rho squared, purity. Purity is, log of the purity is the simplest form of entanglement. So we need to propagate in time two density matrices, which means one forward, one backward branch, one forward, one backward branch. And now, in order to kill all the phases, you have two possibilities. That the backward branch equals the forward branch of the first copy, and the same for the second copy, or you can swap them. So on every unitary, you have these two choices. This is for the Renyi entropy, Renyi 2 entropy. In reality, you need to calculate some information quantity that is real entropy and average it properly. You need to do it for all the number of replicas, all the Renyi entropies, and take at the end replica limit n to 1. So that's why you need all the possible, you basically construct a family of statistical mechanics models for a different number of replicas and have to take the replica limit. But you can understand in a basic way at the level of the second Renyi entropy, where you have two replicas, you can get a good qualitative understanding of what's going on. And what's going on is that you have this effective ferromagnetic Ising model in terms of these replica spins. And the boundary condition at the top basically depends on the quantity you're calculating. If you're calculating entanglement entropy, then the boundary condition is up spins, let's say, which corresponds to the identity permutation on one subsystem, and on the other subsystem, you have a cyclic permutation. In the case of just two replicas, it would be the swap. So what this means is that you need to calculate the free energy of the system with a domain wall, forcing a domain wall to end at the boundary. And that we know has two possible free energies. The free energy can be linear in the length of the domain wall, and therefore linear in the length of the subsystem. In the case of a ferromagnetic, when the model is ferromagnetic, if it's paramagnetic, domain walls are cheap and cost order 1 free energy. And that means that the, so that the entropy, entanglement entropy averaged over the circuit and over measurement outcomes would be either volume law in the ferromagnetic state or area law in the paramagnetic state of these things. So that's like kind of a really nice way of understanding the transition, which is a pretty unusual system using pretty familiar language of statistical mechanics. By the way, from analyzing the statistical mechanics model, it very quickly became clear that there are even nicer, in a way that we'll understand later, much nicer probes of this transition. And if we want to alleviate this post-selection problem, it would be nice to look at these probes. So a nicer probe of the transition than entanglement entropy would be, and we'll see what it maps to in the end in the statistical mechanics problem. Basically, you see that there is a transition between ferromagnetic and paramagnetic state, and here I'm probing it by the energy of a domain wall. It's sort of a non-local probe in the statistical mechanics problem. A nicer probe would be just directly looking at the spin correlations. So to look directly at the spin correlations, you can measure something else. So suppose I have the same circuit, but the change now is in the last time I measure all the qubits except for 2, I and j. Okay? In this case, you can, and now I want to ask the question, what is the mutual information between I and j? Which when the total state is pure is the same as 2 times the entanglement of I or of j. So in the end, you have just a 2-qubit wave function in your hand, and you can ask the question whether it's entangled or not, and that maps exactly to the spin-spin correlation in this statistical mechanics model, which means that in the ferromagnetic state, this entanglement will go to long distances. So these two spins will be entangled no matter how far they are. And in the area law state, though, this entanglement will decay exponentially in distance. Yeah. Yeah, good question. So I'm talking here just for simplicity. Yeah, on one dimension plus one time, but in principle, there are some nice aspects of two-dimensional transitions. Yeah. So yeah, all of this is two-dimensional. Yeah. And here it's one-dimensional, but there is another dimension corresponding to the time. And it maps to StatMech models in space and time. So it maps to two-dimensional StatMech models. So the spins here have nothing to do with the original qubits. They're kind of labels of replicas. The original qubits are gone from this description. Yeah. The spins here are completely classical on the right-hand side. Okay, there is also a really nice understanding that also emerges very naturally from the StatMech description in terms of quantum information encoding. So one way you can understand this transition, this was we pointed out in these papers, so there is one way to understand this as some kind of channel where the input state now is not determined. It's some input state that I want to transmit along this channel, and I want to ask how much of the quantum information that I put in the input survives when it comes out. Why should it not survive? Because this is not a unitary channel. It's because there is some observer, Eve, that is measuring along the way. And in quantum mechanics, when you observe, you also destroy some of the information. And you can ask how much, and this maps in the statistical mechanics model. So how can you ask, what you need to calculate in this case is so-called coherent information from Alice, R here, to Bob, which is at the end, from Alice to Bob, and one can show that this in the statistical mechanics model becomes the free energy of a domain wall that you force in the middle of the system, because the boundary conditions are, say, spin down at the bottom and spin up at the top. And the normalization gives you minus the case where there is no domain wall. And then you see that at the transition between the paramagnetic and ferromagnetic state, you suddenly have what emerges is some finite density of information, quantum information that emerges at the top, right? So you have a phase which is encoding where at least a fraction of the information that you injected at the bottom comes out at the end, despite Eve's intention of disrupting it. And in the area law phase, Eve manages to destroy all that information. So except for maybe order one that remains. There is another aspect for this information perspective, which is the aspect of Eve. You can also ask yourself, how much information did Eve, how much information Eve can extract about the initial state, or the state that I encoded at the beginning. And let's say I encode one qubit here, whether Eve, by doing the measurements, can find that state. And that is quantified by the classical mutual information between the input state and the measurement outcomes, which I call M here. This is a classical information because I'm measuring classically with the same basis. And the maximal amount of quantum information I can get is, suppose I measured every qubit right at the start, I could extract the maximal amount of information about the initial state. So what happens is that initially I get nothing if I don't measure. When I start to measure, I get more and more information, and then there is a phase transition associated with saturation of the information I can gain by doing measurements. And in the volume law phase, some of the information, right, so in the volume law phase, some of the information will forever be hidden from Eve, no matter how long it will continue to measure because quantum mechanics will scramble this information and it will always be hidden. This is, in a sense, these two information aspects show you that this system is sort of a quantum error correction code. When the system is in the volume law phase, it protects some finite fraction of information, and that protection occurs because whoever is the observer that tries to destroy the information cannot fully extract this information. It's partially hidden from the observer. Okay, so yeah. That's the yeah. Oh, the coherent information, the difference is the coherent information is basically SM of Bob minus SM of Bob and M is the measurement apparatus. Some of the information is in the measurement apparatus. So that's why you need post-selection. You need to know the measurement outcome. So how much information came from R to BM minus S of R, B, and M together, right? So this is this is S. This is IC that I wrote here. So well, it turns out that you can show that when M is a classical measurement, so it's completely dephased, M is a measurement apparatus that's classical. So all the information in M is dephased. So there is, I can think of that as SM of the environment because I need to dephase M. There is an environment because M is the measurement apparatus. The measurement apparatus is in a diagonal density matrix because it's being dephased. And this is the coherent information. Now you can show, I won't go over it, but you can show that this is exactly equal in this case when I'm doing classical measurements to the average over the measurement outcome of SMB, which makes sense. Basically, this is just, SMB is how much entropy is left in Bob, okay? So this is different, it has different boundary conditions. There is no subsystem here. You're just looking at the entire, that's why there is no boundary condition. It's all with the plus sign. And there is a boundary condition minus here that comes from this R, the encoding basically changes the boundary condition at the bottom. So I didn't describe why these boundary conditions, but this will take me too long. So, okay, I want to go to a different example that shows more clearly that these measurement-induced phenomena are truly non-local in a sense, and which is what I said. Now the question is, I have a quantum ground state in my hand. I'm measuring some of the degrees of freedom. I know the measurement outcomes, and conditioned on that, I want to ask what are the measurements, what are the correlation functions in this post-measurement state. I'll show that this also has a really nice different mapping to a statistical mechanics model. So again, this is the paper where we did that. This is what we're doing. So here is some quantum ground state. The dangling legs are the qubits in this quantum ground state. And if nothing is measured, then it's in some superposition state, some entangled state. And I'm measuring some fraction of the qubits. After the measurements, there is no time evolution whatsoever. I just leave it as is. And I want to ask, what are the correlations between some remaining degrees of freedom that I haven't measured? How do these change compared to the original correlation functions in the state before being measured? Okay, so here I want to describe a really nice way to understand this problem in a much simpler statistical mechanics model that I think we can kind of understand right off the bat. I don't need any derivation almost. So in order to understand it, I want to, first of all, of course, look at the example of a transverse field Ising model. That's a kind of very simple model that I can go to a critical state. I'm taking it to a critical state. So this is a transverse field Ising model. These are the ferromagnetic interactions, ZZ. This is the transverse field that gives you quantum fluctuations. And now let's forget about the measurements, put it in the critical state. This is, say, my depiction of the ground state, schematic depiction of the ground state. But the more useful way to understand how the correlations in this state will look is, as you know, I can take the wave function of the, density matrix of the transverse field Ising model at zero temperature, the state of the transverse field Ising model, and using a path integral, I can describe it as a 2 + 1 dimensional action, which corresponds in this case exactly to a classical Ising model. Classical Ising model in 2 dimensions of space and 1 time, where the length of the time dimension is the temperature. In this case, we take the temperature, sorry, it's the inverse temperature, take the temperature to 0, so it's infinite in all directions. So this is, I guess most of you know that this mapping from a 0-dimensional quantum Ising model to a, from a 2-dimensional or any d-dimensional quantum Ising model to a d + 1-dimensional classical Ising model. And the correlations I would measure in the state are simply taking the correlations in this classical Ising model on a single time slice. Okay, so for example, the slice tau = 0. Okay, now after this warm up, we can do the same thing with measurements, and it's not hard to convince yourself that basically you have the same stat mech model as before, except on this time slice tau = 0, you have constrained some of the classical spins to the measurement outcomes so if we measured in the z basis, that's the simplest, then we constrain some of these spins simply to be in the z direction. Okay, whatever we measure, whatever outcome we got, they basically are fixed like that. So now we have to calculate a partition function of a system that is fluctuating as before, except there are some spins that are fixed and not frozen and not allowed to fluctuate. We can ask how this changes the correlations in the rest of this slice. So this becomes sort of like boundary critical phenomena. So what I created some kind of defect with codimension 1 inside my higher dimensional system, and that system, and the question is how the correlations on this boundary behave. And I'm going to give a really simple example that shows that there are examples where the correlations change fundamentally. So just by way of example, let's take the simplest case, which is Ising model in 3 dimensions, and then the classical model, effective classical model, is in 3 + 1 dimensions. The reason why this is simple is because then in 4 dimensions we can use the Gaussian fixed point to calculate everything exactly. And the correlation function we want to look at is the correlation function ZZ connected correlation function. Before measurement, it's very easy to calculate. It just comes from simple scaling because it's a Gaussian fixed point, and you can show that this correlation function decays as 1 over x squared. now you can ask, what is the scaling dimension of the operator, this disorder, weird disorder we put on a single boundary, and you find that it's a relevant perturbation. If we measure in the z basis, that gives you a relevant perturbation. What does it mean that you get a relevant perturbation? It means that this slice becomes completely pinned, it becomes, it changes the boundary condition to completely pinning boundary conditions. And now you need to calculate the correlation function in completely pinned boundary conditions. Then there is a trick, completely pinned boundary conditions, the correlation function, the field become now derivatives away from this pinned boundary. So you get an extra derivative for each field. And because of that, you get x to the minus 4 for this spin-spin correlation function. So this changed the long-range correlation. So by doing measurements that are completely local, you can change the critical correlations at arbitrarily long distances immediately, right? So here it's something that happened at 0 time. You change which is quite remarkable. There is another example I can do where instead of measuring in the z basis, I measure in the x basis. And that turns into kind of energy perturbation in a single energy operator perturbation in a single slice. That turns out to be irrelevant. And no matter how strongly I measure, even if I measure almost all the degrees of freedom, I would still at sufficiently long distances find that the correlations are unchanged. Yeah, let me skip over that and go. Yeah, so maybe the upshot of all this is it really exemplifies nicely that measurements, although I do local measurements, I can change the structure of the state at arbitrarily long distances, and that has to do with the fact that the state was entangled and the time evolution imposed by quantum collapse is not burdened by Lieb-Robinson bounds. And the other nice thing is that there is a very nice framework to deal with this theoretically coming from the field of boundary critical phenomena. Okay, but until now, I didn't talk about the big elephant in the room. And the big elephant in the room is that to see any of that stuff, I need to post-select. I need to look at the wave function after many measurement outcomes, and they should, for example, if you look at the correlation function I wrote down here, I can't calculate something like this, averaged over measurement outcomes, without post-selection, because I need to average over measurement outcome the expectation value in a particular state M. And then only after the fact average over M. So first I need to know how to calculate the expectation value of Z naught in M, and that's impossible without post-selection for the reason I explained before. I have about 10 minutes. Okay. So yeah, so let me illustrate how the post-selection problem works a little bit more slowly. I have a wave function. I measure Z, for example, in the Z basis. I measure in some sites. That prepares a wave function that depends on the measurement outcome. For example, I get down, up, down, or 0, 1, 0, 1, 1. It prepares a particular wave function. Now, to characterize this wave function, I want to, for example, probe some observable, let's say x. So if I now look at xi times xj, which is the correlations I want, in this particular wave function, I'll get some outcome, which is the outcome of the operator xi, xj, some eigenvalue of the operator xi, xj could be either plus or minus 1. So that's not really the correlation function. It doesn't give me any information just from one time. I need to repeat, but if I repeat, I'm not going to get the same wave function, psi m. So to probe this kind of operator, xi, xj, in a particular state m, we need to post-select. It's exponentially hard. Now, you could say, what if I'm just lazy and I'll do the simple thing and simply just repeat the experiment again and again, not caring about the outcome of the measurement outcomes? Well, then I'm really what I'm measuring. Then I can use the fact that the measurements are quantum channel. That what I'm measuring then is just the operator xi, xj in the average density matrix, where the average density matrix is the sum over the projectors on the various measurement outcomes of the initial wave function, right? So this is just an expectation value in this average density matrix affected by a local quantum channel. That's set by the possible measurement outcomes. And the local quantum channel has, again, Lieb-Robinson bounds in exactly the same way as unitary time evolution, for a reason that the local quantum channel I can always purify with an ancilla, and it just corresponds to a unitary evolution with an ancilla space. So, yeah, so I really cannot do that. When I do this, I get something completely different. If I average over measurement outcome, I lose all this non-locality that is present in the single trajectory. So I really need to look at some nonlinear averages like this one, but that do require post-selection, but those I can't get. So I'm in somewhat of an impasse. So here is a first try to solve this problem. So this is, for example, this would be a correlation function I'm interested in and can't get. It's x squared average at the end, right? So that I can't get. It's nonlinear in the density matrix. I can't get it. So I'm going to define an alternative linear quantity in the density matrix, which I call quantum classical correlation. So what is this? What is this quantity? This quantity, what is written here is a measurement outcome xm of m. And what is written here is some classical model for the expectation value of the same variable. So what is this? So on the left-hand side, I have a quantum computer that actually runs trajectories. Every time I run the experiment, I get measurement outcomes in this tree of possible trajectories, and I get a state, and then in the outcome state, I do a measurement, and I get a single measurement outcome, xm, which would be either 0 or 1. Okay? This is what I get on the left-hand side. At the same time, I send out all the measurement outcomes to some classical computer that crunches some model. Maybe the model is just a simulation of the system. Maybe it's maybe it's a machine learning model that inputs, it takes these m's and outputs the expectation value of x for this particular measurement outcome m. And this label C means that it's some kind of a result of some classical model or classical computation. And now I just repeat again and again, and in the end take the average. Okay, so average overruns. Really, I should say this average overruns. Okay, and this average is totally fine. This average, I don't need any post-selection. Here I can do this, and note, because I'm averaging over just a single, measurement outcome m, not in a particular state, right? So this is a sample efficient quantity. The problem is not the quantity I wanted, but note that if my classical model, what's on here? If my classical model were exact, then this thing and this thing are exactly the same, okay? But if I don't have an exact classical model, then it's something, at least. In a sense, it gives me a new paradigm. So I'm going to improve on this in a second, but already it's giving me a new paradigm to compare experiment to theory. in traditional experiments, when I want to compare experiment to theory, I have an experimental plot, experimental dots, which correspond to measuring some expectation value of an observable. And I have a theoretical plot, theory plot, which corresponds to just calculating the expectation value of the same observable, and I can check how good my model is by comparing theory to experiment. The problem with these new experiments is that I'm stuck already at step 0. I don't have a way to measure expectation value of an observable. It doesn't make any sense. So I can't compare theory to experiment. So the next best thing is what I showed before. The next best thing I can calculate is quantum classical cross-correlation. This would be what I call the experimental result. And the fully theoretical result would be just to calculate it fully with my classical computer, right? This is the theory. So now I have a new paradigm for comparing theory to experiment. But of course, it allows me to test how good my model is. It's not allowing me to measure some intrinsic property of the system, because both the red and the solid line, they both depend on my model. I'm not measuring something model independent. And the last question I want to ask is whether I can measure something model independent. Basically, here are concerns. One concern is, if exact simulations are possible, what's the point of doing the quantum computation? That's a valid concern here, because we get the exact result only when the computation is exact. And also, if classical computations are only approximate, then what does this object mean? Because it's not really related to any intrinsic property of the system. So it seems like there is some intrinsic property about it, except for the fact that it allows me to test my models. But I really want to learn something intrinsic about the state. And the last part is this. And this is from a pretty recent paper that just got on PRX Quantum with Sam Garrett. So the idea is, we have a system. We're going to have a system. I'm going to measure almost all the degrees of freedom and leave some unmeasured, let's say subsystem A and subsystem B. These could be, in the simplest situation, 2 qubits. And I want to know some properties like the entanglement between A and B. Okay, like entanglement between A and B is trace over B, and then take the trace rho log rho, the reduced density matrix A. I want to know what is the entanglement produced by measuring all these states. This is kind of, the reason why this is interesting is, one reason you can say is for the measurement-induced transition, this is one of the nicer probes of the measurement-induced transition. So what I'm going to show you is that there are these objects, which I call quantum classical entanglement entropies, which are accessible to sample-efficient sampling, just like before, and bound from both above and below. So these are model-dependent objects that depend on the model with which I generate them, but they can be extracted in a sample-dependent way, and they bound from both above and from below the intrinsic property, which is the entanglement entropy I can't get. So this is nice, because now I can actually at least bracket what I want, and I can now try to improve my model and get this bracket to converge from both the bottom and the top. And I can use it as a variational way to improve my model using the quantum data. The way I get it is a little bit technical, but I'll just explain the gist of it. The gist of it is, so you have some density matrix that you want to learn, and every time you get a different one. So this goes according to kind of the philosophy of classical shadows. But in classical shadows, you want to learn about the wave function or about the quantum density matrix rho, that you, by doing random measuring in a random basis. And that allows you to reconstruct this state. It's an efficient way to do quantum state tomography if you want. But this classical shadows requires you to get repeatedly the same state. In our case, we don't get repeatedly the same state because every time we get a different measurement outcome, which means we get a different rho m. Okay, so what we want to get is S of m, which is trace rho log rho. And as I said, this is impossible to get because well, it's nonlinear in the density matrix as before. So what we're going to do is we're going to replace this log rho m, which is the problematic part, it's nonlinear, with a classical estimate, log rho mc. This will be generated by our classical model. And this we want to make into some kind of measurement outcome. Now, this is not a measurement outcome. It's some density matrix. We get a state. We don't know what rho m is. So here is where we use shadows. Shadows is just used like this. We can use if we measure in a random basis, we can have an estimate, a bad estimate of rho m called sigma m, given by the measurement outcome times the unitary used, which is known. This is something we know every time we do the experiment. We measure in a random basis. We can construct this thing. And the nice property of this thing, which is still correct here, is that it converges exactly to the trace of after averaging over measurement outcomes, after runs of the experiment, it exactly converges to this thing, which is trace rho log rho c. So this is something I could get in a sample efficient way without any need of post-selection. And this is what I called SQC, okay? So now we can forget about the shadows. Shadows just means that I can, if I do sufficiently large number of measurements by central limit theorem, I'll basically converge to this. And it allows me to measure this quantum classical entropy. And now I'm going to, well, I didn't show the bound. Yeah, so I wanted to give some, how much time do I have? 2 minutes? 5 minutes? Okay, yeah, that's enough. I'm nearly done. So here is an application. Then I'll show quickly why the inequality. The real nice application is for the measurement-induced transition. As I showed you before, a nice probe of the measurement-induced transition is in this circuit, measure in the bulk of the circuit, but also measure all the qubits except for 2 at the final time. And then ask the question, what is the entanglement between the 2 remaining qubits and how does it change as a function of the distance between them? Where in the area law, it goes down exponentially, and in the volume law phase, it's a constant. If you remember, it basically maps to the spin-spin correlation function in a stat-mech model. Okay, so now we want to calculate this. What we can't calculate this entanglement entropy, but we can calculate the quantum classical entanglement entropy. The upper bound of the quantum classical entanglement entropy can be seen in this way. So remember my definition of the quantum classical entanglement entropy, it was just this thing with a minus sign. And the SM, what I want that I can't get, is just trace rho log rho. This thing here is what is called the quantum relative entropy. It's the quantum version of tail divergence, the difference between the 2 distributions, if you want. And it is known to be larger than 0. So just by this one-line proof, you see that the quantum classical entanglement entropy is larger than the quantity that we want. And using another property of the quantum relative entropy, which is monotonicity, we can show also this lower bound that SA is larger than the same object SQC minus the quantum classical estimator for the entire entropy of A and B. Okay, so actually this means that the really key quantity here that describes you that gives you the size of the bandwidth of between the upper and lower bound is your quantum classical estimator for the entanglement for the entropy of the A and B sites combined, and one can use this to train a model to give you the smallest possible quantum classical entropy of the two-qubit state. And here is an example of running this idea in simulation so far. We're now starting a collaboration to do it experimentally. Here, it's, we didn't have a quantum computer at home. So what plays the role of the quantum computer? I need to do actually exact simulation. And the exact simulation is like the quantum computer. What plays the role of the classical model? The classical model is a matrix product state calculation with chi, the bond dimension of the matrix product state that I can change. And what you see here is on the result of the entanglement entropy of between the two qubits. The circles here, as a function of the measurement rate, are the exact result, because we're also doing exact calculations, so we know the exact result in this case. Above is the upper bound, below is the lower bound. Here, we calculated a slightly different lower bound because we didn't have the other one before, but it's still a very nice lower bound. And you see that what is nice here is you don't see a sharp transition because we could only do very small simulations. You need to do an exact calculation here to compare to this matrix product state ansatz to have the quantum part of the quantum classical. But you can already see that the transition is around 0.16. What is going on in the transition? In the area law phase, your model can converge to the right result, basically, and you can get and you can get the as you increase the bond dimension, you basically converge exactly to the right result, and also the lower bound converges exactly to the right result. And while in the volume law phase, there is no way the model can converge because we need a bond dimension that scales exponentially with the system size, and therefore you see a divergence between the upper and lower bound. Here we show that at the critical point itself, we can actually very nicely get the power law behavior. Yeah, the entanglement entropy as a function of L, the entanglement entropy between these two qubits decays as a power law. As you increase the bond dimension, you see this power law at a larger and larger scale, and you can even do nice scaling collapse by a nice scaling collapse using kind of finite entanglement scaling theory. Won't go over this. So just to summarize, local measurements can have collective non-local effects on entangled quantum states. Observing these effects is really a big challenge because of post-selection. But we have various ways to alleviate post-selection. One of them is to look at quantum classical cross-correlations. And we've shown that certain quantities, when you do the quantum classical cross-correlation, they bound an intrinsic, they allow you to bound an intrinsic property. And specifically for the measurement in induced transition, we can make that upper and lower bound tight with computable simulation. What would be really nice in the outlook is that the model generated density matrix is not generated by a calculation, but imagine we have some machine learning model that is trained exactly in this way. The machine learning model gets as input the measurement outcomes in this particular experiment. It spits out rho C. Initially, this rho C is lousy, and then but it can construct together with this rho C in a sample efficient way, this quantum classical cross-correlation. Should be quantum classical. This is shadow, okay, shadow classical. Repeating this many times gives you the quantum classical cross-correlation. And now we can repeat, if we want to make this as small as possible, so we repeat and optimize the neural network until we get a better model. This is a variational way to find a good classical model without ever doing any actual computation, without even needing to know what are the unitary gates that you're given. So you're learning a state without knowing what are the unitary gates. And actually, we have preliminary results on this. It seems to work really well for the one plus one dimensional system, one dimensional system plus time. It would be interesting to see how it works for two plus one dimensional measurement induced phase transition, because in this case, we don't have any way we know how to classically simulate the system. Okay, thank you very much.
Any question?
So thanks for the talk. In the first part of the random circuit model, is it meaningful to think about replica symmetry breaking in the map, the classical model?
Sorry, the replica symmetry breaking is what?
I mean, is it meaningful to think about this replica symmetry breaking in the classical model you mapped to?
There is a replica, so this symmetry broken state is really like the replica of broken symmetry state. But in this case, it's not usual classical replica symmetry breaking. We have two, in fact, the replica symmetry here, I didn't make it clear, is actually permutation group Sn times permutation group Sn. It's Sn cross Sn, and you break independently the left and right permutation group, which is because it has to do with the fact that in quantum partition, in the quantum density matrix, you have, it's really a matrix, and you have the right, and you can act from both the right and the left, and you have a permutation symmetry for both Ketz and for Braz independently. On the other hand, so this is not exactly the same as classical replica symmetry, which would be an exchange symmetry, that you have n density matrices and you have a symmetry to exchange the entire density matrix. Here we have the symmetry to exchange Ketz independently and Braz independently in the density matrix. But yes, it's a sort of replica symmetry breaking. So the emergence of an volume law state corresponds to replica symmetry breaking, and it's nice. It corresponds to emergence of some coding state, some code space in this emergent error correcting code.
Due to the time constraint, maybe one more quick questions.
In the 2+1D quantum case, is there a phase transition from the different scaling of the magnetic?
Oh, yeah. So good question. In different scaling of the boundary correlations or post-measurement correlation functions. In the Ising model, no, I don't think so, because it's either you make measurements that are relevant or irrelevant, so it basically takes you to a different boundary fixed point. But I didn't have time to discuss, there is another problem we looked at in that paper, which is a one-dimensional quantum liquid, where you can actually tune the decay of the correlations continuously. It's a Latinger liquid. It has a continuously tuned critical exponent. And the measurements are as a function of the tuning of the critical exponent. So for example, this would be a situation where I have quantum liquid and I measure whether there is a particle or no particle in some regions, but not everywhere. Or I measure with some finite probability and ask how this changes the phase correlations or the density correlations in my quantum liquid. And it turns out that as a function of the interaction strength in this quantum liquid, I can undergo a phase transition between measurements being relevant to measurements being irrelevant. And that again corresponds to some kind of boundary phase transition.
Thank you.
Okay, due to the time, so I think let's just thanks for Professor Altman's lecture again.